Okay, so we are going to continue with the next setup, and this setup, it is one way to find the FT of the transistor. So I have already shown how to get the FT of the transistor using a DC operating point, and this is a very simple way, but it is not the only way. The following setup, it is a variation of the self-bias transistor that we have already studied. This setup has a few more components, but the main difference is that it will enable us to run AC simulations. So in the previous setup we could only run DC operating point. Now how do we do the AC simulations? Well, we add the following things. At the drain of the transistor we are going to put a low pass filter, because what we are interested in amplifying is only the DC part. We are going to compare only the DC component of the drain voltage with the VDS that we have here at the right, and send the feedback back to the gate. We are going to add one very large resistor. So this very large resistor will in principle help me to not to load the input. Okay, so the input will be not loaded by the amplifier. The amplifier has very low impedance, so I cannot connect it directly to the input and connect another source at the gate input. So this very large resistor will decouple the input and the amplifier's output. And at the drain I connect a very large capacitor to ground. So the large capacitor will work as a short circuit for high frequencies and let all the AC current pass directly to ground. And then I add a current probe just after the capacitor, so this will be sensing all the drain current that passes, all the AC current. So again, this one for DC operating point, it will do exactly the same as the previous setup, but it will not leak any AC signal to the amplifier. So the amplifier will only see DC signals here. Now the idea to extract the FT is that I will run AC simulations to get all the current gain over frequency, and then we will check in which frequency the current becomes 1. The current gain becomes 1. So for that, what I will do, it is first I will save this setup. I will use the ADXL. I'm going to create a new view. And then I will create a new test. Sell this FT, and I pick at the variables here. And I don't like how it looks this. What are you going to do? Is to call this IDS, because later if I want to use my script, I have IDS1 in the global file, so I shouldn't have the same names in the schematic. So I save, and then let's bring this once again. I can delete this one and then bring, okay, now we are fine. And then we put the default values, for instance 10 micro, the length 180 nanos, one finger, 0.9 volt, and let's say 10 micrometer. And then I want to run an AC simulation. We select AC, start. We are going to start in, let's say, 0.1 hertz. And then let's stop in 100 gigahertz. I'm going to have both the plots. The best is to use a logarithmic scale, so around 20 points should be okay. Points per decade. Put apply, and then the only thing that remains is to set up the output. You can put to be plot, select on design, and then we're going to save this current. Okay, so we check, and then it is saved here. And I think for the moment that's all. So let's extract the the current gain for that amplifier, and we have invalid expression found. Okay, we have by this one. No, it was here. Let's see if we can delete it, and unfortunately, yes, we can delete it. Yeah, so then we run, and then we got our first curve. Okay, so we got the current gain, we put the scale, and we can see that the current gain of this amplifier decreases, and then it hits 1 at around 3 gigahertz for this biasing current. But most probably we don't want to analyze only one current, so we want something more complicated. Let's see if we can change the currents here. So we are going to do something that we have already done before. We're going to sweep the currents, and then we go from to and let's sweep it from, let's say, 100 nanos to 10 milliamps, and then I want to use a logarithmic sweep or decade step per decade, so we can put, let's say, 10 points per decade. Okay, and I check that this has been updated. And we're going to run 8 cores. Let's put 10. We're going to run 10 cores. So we run a quick simulation now, and then we run the simulation, and then we will have current gains for different drain currents. 51 points, so we need to wait a couple of seconds to get all curves. Then we plot them. And then we get all the current gains. Very good. Now I have to find the point in which all these curves crosses 1, and for that I need to use the calculator. So I can open the calculator. I delete this in the here the field for the calculator, and then I can actually bring this directly to the calculator. Let's see, calculator. The calculator is here, so then I have. I can do exactly the same with this one. Okay, select the schematic terminal to create an expression for AC current, so I could have done exactly the same. IF, and then since I am saving this for plotting, so I can check if it works here. I have it in my calculator and it is working. I can evaluate it. Now I need to find a function for this. So what I'm going to do is I have two ways of doing this. One is to get the magnitude or put it in dBs. So let's get it the magnitude first. That will be mag. Okay, I have the magnitude. Let's evaluate it. Okay, I got the magnitude there. Evaluated. And now I will use the cross function to detect the cross. So I got the cross function, and then the threshold value will be 1. Each number will be 1. It will be when it is falling, and a single occurrence. So let's see. See if this evaluates. Oh yes, it is working. And then I got the FT of this transistor for different drain to source current. So as I expected from very low currents, and I can actually put this one in logarithmic scale. For very low currents, it has a very low speed, it has low FT performance, and then it starts going up. And for large currents over 100 microamps, we have already 20 gigahertz FT, and then we peak at some point, and it doesn't make sense to go over this peak to continue pushing current, and that happens for this transistor at around 2.5 milli. That enter velocity saturation and have other kind of problems. Okay, so this is the setup. This equation that I have here, I can import it in my setup. That will be useful. I can right click here, add expression. We can also do it from the ED here from the window, but we can also do it here. Just import it. I can put it a name. I can call it this FT. And then, yeah, I can send it to simulation again. And then FT will be calculated. So now if I right click on one of the FTs and then I put plot all, then I will get it plotted all the FTs. Now finally, I can do exactly the same as I did before. I can go to File, Save Script, and this will be FT. .il, and then I can save it. And then it creates a script. which is very similar than the scripts that we had before. Okay, we're going to copy the script in our folder, so ft here in our folder, and then we are going to open it again in the skill IDE. Now it is a little bit more complicated script because it's coming from the ADXL, that it is a more advanced tool, so it has many more options. But it really doesn't matter, many of the things that we have done are exactly the same. One of the things that we are going to do here is to import our file. That was let's see, we can import the models and the global, so we are going to do it here. I can delete this, and then you can get IDS 1, NF1, BDS 1, and WF1. Okay, and I have to do it again here. And this will be L1, NF1, BDS1, WF1, and then I can even change these parameters, but I will leave it as it is right now. That's it. Let's run it to see if it runs before we start plotting things. Then it starts running, so it is working. Okay, now we have to plot the data, and for plotting we have to do exactly the same as we did before. Put some comments here. And we can use this is the current gain, and we're going to let's say we call AE the current gain. Use this. We know which node we are saving because it is called like this. I prove 0 minus, and it is the same as here. I prove minus result. I calculate the FT, and then I can create a new window. We have a command for creating a new window here, and then we can just plot FT, and yeah, that's it. Let's see if it works. Okay, and yeah, as I expected, I have the FT of the transistor. So now we can just change the size. The size of the transistor, for instance, I have 1.2 micro. Let's put 0.18. Save. Run it again, and then we can extract this curve again. And then yeah, we have the FT versus IDS for this new transistor. Okay, so it's an interesting way of extracting the FT versus IDS curve.